Hello and welcome to EP2P04. This is going to be topic number 7, shear stress and strain and FlexPDE beam solving. This is the second elasticity topic. Let's start off by looking at a differential volume which has a width dx in the x direction, dy in the y direction, and dz in the z direction. You could refer to the outward faces of this thing, the exterior faces of this maybe cube, maybe rectangular prism in general, by referring to the direction that the outward normal points. So this one over here would be the positive y face, or also from its equation, the y equals dy face. This one up here would be the positive z face, or the z equals dz face, whereas the one on the bottom would be the negative z face, or the z equals 0 face. Last time, we defined normal stress as the normal force, that is perpendicular force, so let's say the force in the x direction on the x face, divided by the area over which that force is applied, and we looked at the response to normal stress. So in an otherwise free object, we could say the strain in the x direction is equal to 1 over Young's modulus times the stress in the x direction, but in general, where you have coupling of different axes, then the strain vector is related to the stress vector through the compliance matrix. And we had this result for that allowed us to solve for the stresses, at least if there was only normal stresses involved in the thing, and we set up a situation where that was the case, which involved looking at a differential cube and saying, well, if there's only normal forces on this thing, which means there's only normal stresses in this object, then the partial derivative of the axial stress in any direction is 0. So partial derivative of the x-directed stress in the x direction, that is 0. And partial derivative of the y-directed stress in the y direction is 0. But this time, we're going to be exploring a better picture than that by including shear forces. So this, again, is only true if we don't include those shear forces. That is a force on the x surface, not in the x direction, but a force on the x surface in the y direction, or a force on the x surface in the z direction, or maybe on the y surface in the x direction. Yeah, so those are all shear forces, which will lead to shear stress, and then shear strain through Hooke's law for shear, and a couple of other interesting things. So we'll define what pure shear static equilibrium means. This is if you have only shear stresses and you set up the situation so that that's the case. Then why shear stress turns out to be symmetric, that is the stress on the y face in the x direction ends up always being equal to stress on the x face in the y direction, at least at any point. And how locally any object in static equilibrium requires not necessarily this condition, but that this different partial differential equation involving not just the axial stress but the shear stresses is 0. And then once we have this, we'll practice finding the shear stress, deformation, etc. in both FlexPDE and Maple. Maple, what we're going to be doing this week is only going to be applicable for a situation of uniform loading. So some setup where the problem is going to have the same shear and normal stresses everywhere in the object. So you set it up so that it has the kind of symmetric and uniform boundary conditions in the right way to lead to uniform stress and strain internally. It's not always going to be the case, but when we do set it up like that, we should be able to get Maple to predict the result too and agree with our finite element method solver. So let's do an example with simplified definitions in a special case, and then we'll kind of generalize things later after we get a little bit of practice with these terms. So if you have an x-directed force on a y face like this, so a shear force on that face, then this would be giving us the tau yx, the shear stress on the y face in the x direction is that force, the shear force on that face, divided by the area of it. So this tau yx would be F divided by AY, because this is a y face and this is a force in the x direction. So this means stress on the y face in the x direction. This is going to cause a strain, which is the ratio of this x displacement per step in y. So it's the total x displacement at the total length, but it's really the ratio of those two, gamma. So gamma yx is delta x over Ly. For small strains, that's approximately equal to the angle, shown here as just gamma without a subscript, because the tangent of this is approximately equal to this itself, and the tangent of this is equal to delta x over Ly. At least the tangent is approximately equal to that angle, as long as the angle is very small. Okay, so how is the shear strain, this angle, or more generally the ratio of this to that, related to the shear stress that we applied? Well, through Hooke's law, it's related via the shear modulus. So shear stress, Yx, is equal to G times gamma Yx. Yeah. Now, the shear modulus turns out to be related to Young's modulus and Poisson's ratio for an isotropic material, at least, by this. G is equal to E over 2 times 1 plus nu. So if you have no Poisson's ratio at all for like a material like cork that has pretty much 0 Poisson's ratio, then you end up with G being E over 2. For a material with a larger Poisson's ratio, then G is going to be smaller. So the bigger the Poisson's ratio, the lower shear modulus is, other things equal. And that means the less the resistance to shear stress in causing shear strain. You would get more shear strain for the same shear stress if the Poisson's ratio is larger. So then, seems like it makes sense if you apply a force up and a force down like a normal force, you get it to stretch and extend in that direction and compress in the other ones. If you apply a sideways force, then it's going to go from a square into a parallelogram, right? All good. So the parallels are pretty straightforward compared to the axial stress. We have sigma equals E epsilon, and we have tau equals G gamma for shear. But there is a bit of a problem here. The appearance of these two forces doesn't actually let this thing be in static equilibrium, right? This is going to cause it to spin. So we'd have to balance it somehow. How do you balance it? If you balance it with a moment, which is what would happen if you just fix the bottom and apply this force to the top, we'd have a reactionary force and then a reaction moment. Then it's not actually going to do this deformation we're showing. It's going to bend. It has a combination of bending deformation from the moment and shear deformation from the appearance of these two forces and the shear stresses that show up. So to really get the deformation that we're showing, you need to have the thing in pure shear static equilibrium, which means you apply complementary forces on the side to make the shear stress on the x face in the y direction the same as the shear stress on the y face in the x direction. So this is shown here for a square, which gives the same force applied on the side faces as you had on the top faces to put it into equilibrium and cancel the couples. But if it's not a square, right, like imagine it's a rectangle, then we would have a different force applied on the side in order to create the same couple. Let me show you what I mean. If we take, let's imagine we've got a square here like that, and we have another one like that. Suppose that this one is twice as high as it is wide, and this one is twice as wide as it is high. So let's imagine we've got a force on the top face, which is F, okay? Now, how much force do we need on the bottom face for this to hold still? Well, we need also F. But if we want this to not rotate, we have to apply a different force on the side, right? So now how big do these forces need to be? Let's think about it. This one here is twice as far away from the other one that it's creating a couple with as these ones are. So we're going to have the same couple on these ones on the side if they have a strength of 2F, right? Now what stress does this correspond to? Well, if this is area 1, then these sides are area 2. So we got 2F over 2 times the area, and we get the same stress on the sides. So that means for this to hold still, even though you have double the force on the sides to get it to hold still, you end up with the same shear stress, the same shear stress magnitude on the side and the top as, on the side as on the top, right? So that's why we can say that pure shear static equilibrium means that we need to have applied the same stress on one side as we did on the complementary side. Not necessarily the same force, but yes, the same stress. Okay, let's talk about sign convention a bit. We've been mentioning that tau yx is the stress on the y face in the x direction. Yes, so this is on the positive y face in the positive x direction, and that happens to be equal to the stress, if the stress isn't changing, is uniform. Tau yx also represents the stress on the negative y face in the negative x direction, right? You can see that here shown on the negative y face. What about tau zy? Where are the two tau zys? Well, that could be the stress on the positive z face in the positive y direction, or tau zy could be the stress on the negative z face in the negative y direction. This is not actually new. This is also the case for the sigmas we were dealing with, right? So sigma y could be the stress on the positive y face in the positive y direction, or on the negative y face in the negative y direction. Just like the fact that for the exact same reason that you had to reverse the stresses when you're talking about one side versus another side for these internal forces per unit area, you also have to reverse the shear stresses when you're talking about one side versus the other. It's convenient to think about the negatives just kind of canceling out. So sigma y could mean either positive y face positive y direction, or negative y face negative y direction, as the two negatives cancel. And same thing for the shear stresses. So tau xz could be the stress on the positive x face in the positive z direction, or the stress on the negative x face in the negative z direction, this one back here. Just like with the normal stresses, these could be positive or negative, no problem. We're not going to go and redraw them or change the default directions. By default, if they're positive, that means they are, so here, pointing away from the surface for tension and in for compression. Compression would mean negative stress. We don't have the concept of tensile or compressive shear stresses, but positive and negative still do tell you the directions. So if tau xz ends up being positive, that means that on the x face, there's a force per unit area in the z direction, kind of sliding this face up and the back face down. Whereas if it's negative, then it would mean it's sliding the front face down and the back face up. So this is always going to be true because of the fact that they're internal forces, right? When you're talking about on the positive x face, you have a direction for the force that you've assigned, and that's the same as the force on the opposite face in the opposite direction at any point. So the stress, if you just say sigma x is positive and someone's like, okay, what way does that point? You say, well, on what face? On the positive face, it points in the positive direction. On the negative face, it points in the negative direction. Yeah. So the stress sign by itself doesn't tell you what direction it points to plus or minus 180. Well, it does to plus or minus 180 degrees. It doesn't tell you whether it's in the right direction or the left direction, unless you also know what face you're talking about, positive face or negative face. Notice also that the shear force we defined before was the shear force, this V, was on the positive x face in the negative y direction. So this is related to negative tau xy. Here, we're going to be, just keep that in mind when you draw out the shear forces across beams, that if you want to relate that to the shear stress, tau xy is defined as on the x face in the positive y direction. So it's actually going to be negative this V we were dealing with before divided by AX. All right, let's look at an example. A 10 centimeter cube with one face glued to the table is put into pure shear with shear stresses on the x and y faces given by Fyx equals 10 newtons equals Fxy with directions shown below. If the cube is made of plastic with E equals 1 gigapascal and nu is 0.4, determine the shear stress, shear strain, and the lateral distance the top face of the cube displaces relative to the bottom face. Okay, which side is actually glued to the table? It looks like in the picture it is the negative y face. If it was the z, one of the z faces, then it wouldn't be able to deform into this shape. The z face has to be clear to slide along the xy plane for this to be able to be possible. So we have, let's say, the negative y face here glued to the table. So this is a reactionary force there, and we're applying those forces on the other faces to put it into pure shear static equilibrium. Okay, so let's get started here. We've got a 10 centimeter cube, so that means L is equal to 0.1, and the area would be L squared. So we can say that the force is going to be able to let us figure out the shear stress. So tau, let's say y in the x is equal to the force y in the x divided by the area. Well, area of y. Okay, so force y in the x is equal to 10, and this is the same as force x in the y. And the area of the y face is just L squared, because it's a cube, so area of all of the faces are the same. Okay, so the shear stress would be 1,000. 1,000 what? We had force divided by area, so 1,000 pascals, 1 kilopascal. Shear strain, we're going to need to figure out the shear modulus first. So the Young's modulus is equal to 1 gigapascal, 1e9, and the Poisson's ratio is 0.4. So that means G is equal to E over 2 times 1 plus nu. So 3.57 gigapascals. And, wait. It's smaller than the Young's modulus. So that doesn't make sense. So G is 0.357. Read that wrong. 0.357 gigapascals. 357 megapascals. All right. So now we can figure out gamma. Gamma yx on the y surface in the x direction would be equal to tau yx divided by g. Okay, so 0.28 times 10 to the negative 5, or 2.8 times 10 to the negative 6, yeah? All right, so then the lateral distance the top face moves relative to the bottom face, this was equal to this delta x divided by that amount this y displacement. So that means delta x should be equal to gamma yx. So gamma yx, right, is equal to delta x divided by ly. So if we just take this and multiply it by L, we'll have how far the top surface has moved. Okay, so it's moved by 0.28 microns. So 0.28 micrometers is the displacement of this top surface. Very small displacement. So kind of picture this. 1 gigapascal is like a hard plastic kind of Young's modulus. And we take a 10 centimeter cube of this, pretty decent size, and we go on the top surface and we push on it with the weight of 10 eggs. It moves this extremely small amount of 0.28 microns. So very small displacement of this top surface in shear, even though we're putting kind of a decent force on this thing. So even though this 280 nanometers, this 0.28 microns is quite small, it's actually larger than we would have gotten if we had just applied a normal stress that was the same magnitude as this shear stress. So if we applied this force not parallel to the surface, but perpendicular to it, and didn't apply the side forces anymore, but just this one and then the force on the other side, we would have had only 100 nanometers of displacement because the Young's modulus is larger than the shear modulus. All right, so let's get into some shear stress details. Shear details and proof of shear symmetry in 721. So consider an infinitesimal volume. We've got this really small volume. We have the different shears lined up on different surfaces by the directions that we were laying out above. So tau y in the x direction would be the one on this surface that's in this kind of light purple color there, and sigma y is on the y face in the y direction, etc. Okay, so let's let the back face actually be position x, y, z rather than not necessarily the origin, like this spot there, and then the top right corner here would be x plus dx and y plus dy in the y direction, and z plus dz in the z direction. So that's the coordinates of this face. So you can still say that each of the sides are length dx, dy, and dz. We have this differential volume here. What we're going to do is look at what's required for the net force to be 0 when we consider all of the shear and normal stresses and the forces they produce together on this infinitesimal volume. Just to preview what the end of this is going to be, the net force equaling 0 is going to lead us to this set of differential equations. So rather than just that del sigma x by del x equals 0 and del sigma y by del y equals 0, and same thing for z, we've got this combined thing, del sigma x by del x plus del tau yx by del y plus del tau zx by del z has to equal 0, and something similar in y and z. Then by looking at the net torque equaling 0, we're going to determine that the shear stress has to be symmetric. At any individual point, tau xy is equal to tau yx. So the net force on, let's say, the positive y face would be the stress, the normal stress at y plus dy, that's the coordinates of this face, times the area of that face, day, which is the x length of this volume, so dx times dz. That would be day, that's the area of this face, dx times dz. Okay, so then the total force on this face from the normal stress alone would be equal to dx dz times sigma y at y plus dy. While we have a normal stress on the negative y face producing a force in the other direction, which would be the same area, dx dz, times sigma y at y, because that's the location of this face. So sigma y at y is the stress on this face in that direction, and sigma y at y plus dy is the stress on this face, which, because it's on this face, is in the direction to the right. So the net force would be the sum of those two stresses, given that one of them is in one direction and the other one's in the negative y direction, each times dA of that face, which is dx dz. So in total, from this stress and this stress, we have a net force in the y direction that's given by this. So dx dz times sigma y at y plus dy minus sigma y at y. And as before, we can say that the difference in these two stresses by a linearization leads to this quantity here. So what do I mean by a linearization? Well, that means that if you're going to evaluate any function at y plus some small amount, then you can say that this is equal to like a one-term Taylor series approximation, sigma y at y plus del sigma y by del y at y. So like evaluated at y as well. Sort of a strange notation you could use for this. Maybe we'll say at y equals, or I don't know, I guess it's at y, right? So del sigma y by del y at y times what? Times dy. Plus, it would be the second derivative. So second derivative of this thing evaluated at y over, what is it? Over 2 factorial times dy squared plus etc., right? But all of these extra terms don't matter, and neither does the dy squared, because that's going to be negligible compared to dy, since this is already very small. We're looking as we take things close to 0, then this is basically just the first 2 terms of this, right? And when you then take this thing and subtract off the sigma y, you're left with just this quantity. So that's what's left there, right? We end up with, let's say, we end up with just this thing because the linearization so we'll say the linearization of sigma y at y plus dy when we subtract sigma y at y will lead to just del sigma y by del y dy as follows. Okay. Right. So there we go. And I guess we could put in that thing. Therefore, this minus sigma y at y will be equal to this thing minus just that first term, right? Which equals this thing. Yeah. Okay. So there we go. All right. So we'll just kind of comment this out. Got that macro that turns text to green that I made a long time ago and is still kind of useful for formatting stuff. All right. Anyway, what do we have? The net force in y because of the normal stresses is then dx dz times the slope of sigma y and y times dy. This is something we derived last time when we were looking at just normal stresses and the forces that they make on an infinitesimal volume. So this time, the difference is we're going to notice, hey, you know, that's not the only place we can get stresses. Well, we can get forces in the y direction on this thing. We can also get forces in the y direction from tau z in the y, or tau x in the y on the top and bottom and front and back surfaces, respectively. So if we do something similar, then we're going to say, you know, what would be the net force in y from tau zy? It would be tau zy at this surface times the area of that surface minus tau zy at this surface times the area of that surface. So we're going to get tau zy at z plus dz, that's the location of the top surface, minus tau zy at z, the location of the bottom surface, because that one's in the left direction, the negative y direction, and multiply by the area of that surface, which is dx times dy. So dx dy times this difference in shear stresses using the same linearization trick is going to lead to del tau zy by del z times dz, the step in the z direction. Okay, and if we were to figure out the net force in the y direction from the shear stress tau xy, it'll similarly be tau xy at x plus dx minus tau xy at x times the area of this face, which is dy dz. All right. And when you take the difference in those shear stresses, that'll lead to tau xy's partial derivative in x times dx by, again, the same linearization. So in total, we're going to have a dx, dy, dz in every single term, right? So this one, yeah. And you can factor that out, and we're left with the partial of tau yz with respect to x. Oh, actually, I guess this is... Sorry, did I say yz? Yeah, it says tau yx here, but actually, I guess, although it's going to turn out that that's the same thing, we haven't really worked out that that is exactly the same for now. So we should technically say the stress in the y direction. Stress on x in the y, its slope with respect to x, and stress on the y face in the y direction with respect to y, and the partial derivative of the stress on the z face in the y direction with respect to z. So then, the net force per unit volume, because this is the volume of that infinitesimal rectangular prism, the net force per unit volume would be just this thing. Yeah? So the sum of these three derivatives. The partial of the xy stress, xy shear stress, and the y normal stress, and the zy shear stress with respect to each of their directions. If we were to repeat this on the faces that give us forces in the x direction, so the faces with the faces and stresses that give us forces in x, we would get something that looks like this. And for the forces in the z direction, we would have this one. Again, kind of similar. You've got the stress in the x with respect to x on any face that would give stress in x with respect to x. So the x faces in the x direction, y faces in the y direction, z faces in the z direction, and all for the stresses in the x direction. Remember, the last index of each of these tells you the direction of the force, and the first index tells you the face that it's on, right? So the sigma x just has one index, so it's both on the x face in the x direction, whereas these ones are on the y face in the x direction, on the z face in the x direction. Yeah. So equilibrium then, we would just lay out these three equations in matrix form and assert that the force in the x direction, which was this first one, has to be 0. Force in the y direction per unit volume, the second one, has to be 0. Force in the z direction per unit volume has to be 0 as well. So we've got this condition. Instead of needing the partial of just the normal x stress in the x direction to be 0. We need this sum of that partial derivative of the x stress and the partials of the shear stresses that give force in the x direction to be 0. So the force equation, saying that the net force on this thing is equal to 0 because it's not accelerating in any direction, has led us to a coupled set of 3 partial differential equations in all of the normal and shear stresses. Now that's not going to be enough to solve for everything because we've got 3 different axial stresses and 6 different shear stresses. So we've got 9 unknowns in only 3 equations. So that's not going to help. We need more information. Okay, so one way to help is with the torque equation. We can get 3 more equations from saying that the net torque is equal to 0. All right. Well, let's figure out what the net torque equaling 0 tells us. First of all, on any face, for an infinitesimally small volume, the stress is not changing. So del sigma y at every part of this face is the same. We're looking at a volume that's small enough that the stress is not different at this part of the face or this part of the face or this part of the face, because it's all the same part of the face, right? Even though we're drawing it kind of big, it's really an infinitesimal volume. We can always look at a smaller volume so that the stress is not different on one part of it than another part. That's going to be true as long as the stress is continuous, and for any physical situation, it will have to be. Okay, so the stress is the same on this part of the surface as it is on this part, and that means that the sigma y doesn't produce any net torque, right? Because we don't have a difference at the top or bottom of this, so it can't actually create a couple on this face, and it's not going to create a couple with this one because they're both the same over the face, so they're collinear and don't produce any net torque. But the shear stress pairs do, right? The tau zy and tau on the top surface and on the bottom surface here are in opposite directions and displaced by they don't have the same line of action, right? So this creates a couple. In fact, they are perpendicular to their line of action here, which has a length dz. So these two will create a torque given by the magnitude of the stress times the area to tell you the force that it produces times dz. That's the moment arm. And what way is that torque? By the right-hand rule, you can see tau zy would make it spin like this, and that is in the negative x direction. So they create a net moment in the negative x direction, moment because it's a couple, right? So the same torque about every point. That is the area of the top surface, dx dy times tau zy, that's the force, multiplied by the distance between those two lines of action, which is dz. So that's the moment created by the zy shear stress. Similarly, the xy shear stress we're showing here would create a net moment in the positive z direction, given by tau xy times the area of the x face, which is dy dz, multiplied by the distance between those two, dx, and the shear stress itself. So we've got dy dz times dx, the moment arm, times tau xy, which is the magnitude of that shear stress. So we have moments created by the shear stresses. All right, so just to recap, the shear stresses create couples, and so when we're finding the net torque on this thing, we're going to have to consider the shear stresses, but the axial stresses do not, so we don't need to consider those when finding the net torque on this infinitesimal volume. The net torque in the x direction, for example, will involve tau zy that we just saw. This creates a moment in the negative x direction, and tau yz will create a moment in the positive x direction. So the net torque about the x-axis, for example, will be the moment arm dy times the force created by this shear stress. So that'll be tau yz times the area of that face, which is dx and dz, multiplied by dy, the distance between them. And then the moment produced by tau zy that we figured out above is dz, tau zy, dx dy. So there's the same volume element in each of these. And we've got that the net torque in the x direction is dv times not slopes of these things, but just the raw difference in this shear stress and this shear stress, right? So that means the net torque about the x-axis is per unit volume from these couples is tau yz minus tau zy, just the difference in those two shear forces. Unlike what we had above, where we said the net force in the x direction is this differential equation on those things, and we had some kind of flexibility there. Now we only have one option. The only way to get the net torque about the x-axis to be 0 is to have that the yz shear stress on this infinitesimal volume is equal to the zy shear stress. Similarly, if we were to look at the net torque in the y direction, it's going to lead us to tau zx is equal to tau xz, and the net torque in the z direction being 0 is going to lead us to tau xy equals tau yx. So that means that the shear stresses at any point have to be symmetric for you to have no net torque acting on an infinitesimal volume. So that's why the shear stress is symmetric at any point. The reason that the xz shear stress is equal to the zx shear stress, for example, is because the only moments in the y direction produced on this thing are from those pairs of shear stresses. And if you want there to be no net torque on this object, if it's in static equilibrium, then you have to have that those two stresses are equal for the net torque in the y direction on this infinitesimal volume to cancel. You can't have other applied moments on this thing on an infinitesimal volume because the stresses cannot change over the infinitesimally sized surfaces. So the axial stresses don't contribute, and it leads directly to this symmetry in the shear stresses. Review question for you. Let's suppose we have this macroscopic object and it's subject to an externally applied shear force on the top surface and the bottom's fixed. So we're going to have a reaction shear force and a reaction moment to hold it still on the negative y face. Is the stress symmetric for this object as well? It is, but it's not uniform. So the stress on the top surface is not the same as the stress on the side surface, but that's because but at any point, tau xy is equal to tau yx. So along the side surface, we have no, the x surfaces here. This would be the negative x surface, this is the positive x surface. We have no force applied in the plus or minus y direction because it's a free surface. So that means that the stress on x and y has to be 0 here, but because the stress is symmetric, it also means the stress on y and x is 0 here too. So the stress up here, yx on y in the x direction, which is definitely non-zero because we're applying this shear force, is not going to be equal to the stress on the side because it's a free surface. But at any individual point, we'll still have that tau xy is equal to tau yx. Okay, now we're going to talk about true strain, and this thing is scary. It looks terrifying, but don't worry, it's not as bad as it looks. All we're looking at is we're going to say that we've got some initial position, which is xy, and then it's dx size in x and dy size in y, looking at this little element here in 2 dimensions, and we're going to suppose that it has some displacement u in the x direction and v in the y direction. But the displacement could be different at every corner in general, right? Because it's going to move and also deform and all that. So the displacement of the top right spot would be u at x plus dx, y plus dy. That's just at the coordinates of the top right spot in the x direction. U is its x displacement, and the y displacement would be v at that same spot. So we got v at x plus dx, and y plus dy would be the y displacement of that spot. Okay, so that's just what we're talking about. This is just like the displacements of these different things. The angle change of the sides, you could have like the top side change by an angle and the bottom side change by an angle. We're going to call like alpha. This is the change in the horizontal bottom surface, and beta, the change in the vertical surface, the amount that moves in. Previously, it looks like the gamma that we defined at the beginning was equal to just this beta, the one on the side there, right? But that seems a little bit strange, because what if you just take this thing and you rotate it up a bit, and you've got all the displacement down here as this angle, like it was this side that's fixed instead, right? So this is a way to account for that and deal with the difference. We're really looking at the change in this angle versus this angle, yeah? Now, if the thing just rotates, we can be deceived because we'll have a large beta angle, which is showing up from the thing rotating around, even though alpha is negative. There isn't actually any strain in that, right? So what we're talking about is strain, the one that is related to the stress that shows up over the shear modulus, shear strain, is actually the sum of what you would have, what you might call the true shear strains, where true shear strains are defined as just the slopes in displacement. Remember we said that the axial strain, the normal strain, we figured out last time, is actually the slope in the displacement with respect to that given direction. So that axial x strain turns out to be the rate of change of the x displacement, u, per step in x, yeah? So this way, if the object moves and changes size, you're accounting for what you're accounting for that movement by subtracting off what the displacement would have been at some point a little bit before. So the x axial strain is the slope of the displacement in the x direction with respect to x. Similarly, the true shear strains, epsilon yx, this would be per step in y in the x direction, is the slope of the x displacement with respect to y position. And so let's see what that would be talking about here. We've got how much the u is changing per step in y. So it'd be the difference between the displacement at the top side in the x direction and the displacement at the bottom side in the x direction, yeah? And so top versus bottom is where the dy is coming from, the per step in y, and x displacement. So we're always looking at u, the displacement in the x direction. Then the true shear strain, that's kind of the pair of this one, is the y displacement change per step in the x direction. This is not guaranteed to be equal to this thing, right? Because the thing can rotate. So if we have a rotation, then we'd have let's see, per step y that we go up if we're rotating in the clockwise direction. If we look at a point farther up, then it will have moved more to the right. So we'd have del u by del y is positive. But what about this one? If we look more to the right, it will have moved down if it just rotated, yeah? So then we will have del v, the y displacement per step in x, is negative, yeah? And if you add them together, if it's just rotating, then they'll cancel. And that gives a hint at how you find out the engineering shear strain. So the engineering shear strain, the one that's actually related to the shear stress per shear modulus, is the sum of these two true shear strains, right? These like mathematical ones that are saying how much the object has actually, how the displacement of the object depends on position. So if you wanted to build in some relationship in your finite element method solver, which we're going to do soon, that relates the shear strain to derivatives of displacements, you really would not use just epsilon xy or epsilon yx. Those things are not equal. You would instead say that the sum of those two things is what's related to the shear stress per shear modulus. So that brings us to where we can make a Hooke's law for shear. Before, we said that the full Hooke's law, considering different axis coupling for a material, relates the stresses in the normal directions to the strains in the normal direction via this matrix here. So what matrix would that be? It's the compliance matrix, because higher compliance will mean more strain for a given stress. So this is the one that we have the symbol S for because of that weird non-intuitive symbol assignment that we're using in statics. Okay, now for shear, there's in an isotropic material anyway, no coupling from one shear axis to another. So that means the YZ shear strain is just the YZ shear stress divided by the shear modulus. And that's great. So this is what's going to be the source of the other kind of missing equations that we had. We had extra information from the fact that the shear stress is symmetric. So it's not actually 9 unknowns in this. It's just 6 unknowns. Then we have extra equations coming in to help us out from the elastic definitions and the relations between the stresses and the displacements. Once we also combine this stuff, the Hooke's law, with the derivatives of displacement in each direction. To summarize all of this stuff that we've been deriving, we found that locally Newton's second law, the net force being 0 and net torque being 0 for a material in static equilibrium, leads to coupled partial differential equations for the normal and shear stresses, requiring net force on an infinitesimal volume to be 0 is what led to this one, and symmetric shear stresses. This came from requiring no net torque on an infinitesimal volume. Then we related the strains and displacement for both the normal strains and the shear strains, where shear strains are the sum of the true shear strains in each direction. So the YZ engineering shear strain is the sum of the ZY true shear strain and the YZ true shear strain. Because the engineering one is the one that's related to stress via the shear modulus, this is the definition that we're going to use every time. Now, in these definitions, U, V, and W are the displacement in the X, Y, and Z directions respectively due to some deformation. So because of the stress that we're applying, we're going to have some deformation of the object, U in the X direction, V in the Y direction, W in the Z direction, and this displacement is not going to be the same at every single point. But given how the displacements are changing across the object, we can figure out what the strains are, and by using Hooke's law, we can relate those strains to the stresses, and we can relate the stresses to each other via Newton's second law. Now that we have these new relations, we can modify our FlexPDE code to work more generally for elasticity. So let's do that. I'm going to start with the code that I used in the FlexPDE tricks video. This is a normal elasticity set of code. So we've got our displacement variables put in there already, and we've got this little trick to make the deformation always show up quite prominently for whatever it is that we're looking at. And we can set up the thing to deal with perhaps one of the problems that we dealt with earlier. So we looked at a 10 centimeter cube and we put a force on the top surface. So let's do that. We'll put the length in each direction to be 0.1, and this is going to draw out a cube because of the code that we've got down before. We're taking it in the X direction up to Lx and 0 and Ly, Lx, Ly, and then let's just draw this out. So what are we doing? We're starting at 0, 0, and then we're going to go over to Lx, 0, and then up to Lx, Ly, make the Y coordinate go up. Then we're going to go back to 0, Ly, yep, and then we're going to go back down to 0, 0. And we can apply the loads that we're looking for already. So we had to have a stress of 1 kilopascal. Maybe we'll call this S applied. It's not actually case sensitive, so the positive A doesn't really, the capital A doesn't matter here, positive A, capital A. So we'll call this 1E3 for the applied stress. And actually, maybe we'll write in where this comes from. This is 10 over Lz times Ly. So the force that we're applying on the top divided by the area of that face, which is Lz and Ly. Right. Wait a minute. No, the top face is Lz, Lx. It doesn't matter because they're all the same, but it is, if it's a Y face, then it has the area of Lz times Lx. Okay, so that's stress applied. Now, how do we apply the stresses on the right surfaces? We'll say that the bottom surface here is totally fixed. So not just value of v is 0, but value of u is equal to 0, value of w is equal to 0. We'll get rid of that on the back face. Remember we said that the z faces have to be free for this to work. So we'll get rid of that boundary condition, and it will default to the no load boundary condition, which means no stresses on the front and back surface. Okay, so next up, what we'll do is apply the correct stresses on all of the different surfaces. So on the right side, we're going to need the load in the y direction to be S applied. And we're going to need all the other surfaces to be free. So we'll say load U is 0, load V is S applied, load W is equal to 0. Okay, and this will be what takes place from this point where we had Lx0 until the next point, Lx, Ly. So this is the surface x equals Lx. Yeah. Next up, we'll apply a load on the top surface. So on that top surface, we need what? A load in the x direction of S applied and no load in the other directions. So no stresses in the other directions. Then on the left surface, which will be between 0 Ly to close, that's why it's the code that we put here, we will need no load in the x direction, no stress in x, no stress in z in or out of the page, and we'll need just a stress in the negative y direction of S applied. So far we haven't changed the rest of the code, so this is not going to work, right? We haven't figured out how to deal with shear stresses in our differential equations yet, so this should definitely not work. Let's see how it behaves. All right, so I had a bit of a break in the video there. I ran the program and I had to force quit it, but I'd like to show you how this works in case you want to see the way to deal with FlexPDE yourself. Okay, so let's try. This is code that will definitely not work, and let's run it. So it's taken a while, and there we go. So this time it didn't fully crash. It just gave us some deformation, and it's not the correct deformation. Somehow it ended up doing something, but let's look at what the displacement is. The magnitude of, wow, look at this volume change. Volume change of like billions, right? The value of U has gone over by 1 million. So we have like 2 million displacement in the x direction and 2 million displacement in the x direction at the other side. So this is very odd, right? Even though we're supposed to have no net force on this thing, we have displacements in the millions of meters. Something is wrong for this 10 centimeter cube having a 10 Newton force on it. And the thing that's wrong is we haven't dealt with how to respond to those shear forces in our differential equations. So how do we modify the code then so that it will work correctly and give us the 280 nanometers of displacement and the 2.8 E-6 shear strain rather than this value in the millions? Well, we're going to have to incorporate, for one thing, the full set of differential equations that involves shear. Okay, so let's put that in. Just for the sake of symmetry in FlexPDE, rather than calling it like tau yz, let's call it SYZ and use the second subscript to deal with that. Okay, so in the differential equation, we'll have not just the slope in the x direction of Sx, but we'll have the slope in the y direction of Sxy plus the slope in the z direction of Sxz. Let's put them all in alphabetical order so we don't kind of mess them up later. Now down here, we won't have just slope in y of Sy. We'll have slope in x dx of Sxy plus that, and then plus, how to space this out correctly? I guess that's okay. Plus the slope in z of Syz. Right. Now for w, we'll have dx of Sxz plus dy of Syz plus dz of Sz. So that's one thing that we're going to have. And that's all good. That's going to deal with the right stress now. But the code is not going to work because it doesn't know what S, X, Y, X, Z, and Y, Z are. So it says undefined name. Fortunately, it doesn't give us a logic error like the other code did. It gives us a syntax error saying it has no idea what this thing is. So now we have to put in the definition of that, and the definition of that we're going to get is from Hooke's law. So just like we defined the stresses in the axial directions via Hooke's law through the stiffness matrix components, we're going to be defining the stresses in the shear directions via the strains and the shear modulus. So we'll say that this is G times gamma. Let's say little g. Unfortunately, little g and big G are the same. So we're going to give subscripts to this. G y x y s x z is equal to G times G x z, and S y z. Actually, maybe we'll put this in the same order that they are up here. The syntax is you kind of write them in the order of the axis that's not there. So the x1, the one that's in the first component, will be the one that is perpendicular to the x axis. So we've got the stress in yz is equal to G times gamma yz. Stress in xz, that's perpendicular to y, is going to be G times gamma xz, perpendicular to y again. And stress in the xy direction, shear stress in the xy direction, is gamma times, is G, big G, shear modulus, times gamma xy, perpendicular to z. Okay. Well, you can probably guess what's going to happen now. Even though we've defined the stresses, this still isn't going to run because it doesn't know what these symbols are. So when we try to run it, it says undefined symbol G. We have to put that up here. Shear modulus is E over 2 times 1 plus nu. And now it doesn't know what gamma yz is, or xz or xy. Well, we're going to define those in terms of the displacements as well. So that's what this definition was for. Gamma yz is equal to dz of v plus dy of w. Then similarly, gamma xz is equal to the partial in the z direction of the x displacement plus the partial in the x direction of the z displacement. And gamma xy is the partial in the y direction of the x displacement plus the partial in the x direction of the y displacement. And just check that we haven't made any mistakes. So there's some nice symmetry going on here. Looks all good, and that might do it. So we've incorporated this new condition. We've incorporated this by just writing out the stresses in a way that has always called them xz, whether we were actually talking about a force in the z direction, like in this equation, or a force in the x direction, like in this equation, kind of pre-defining the fact that those are the same stress. And we've incorporated this by writing out this set of partial differential equations. We incorporated this already. We incorporated this one by writing our shear strain definition in terms of displacement derivatives. And we've incorporated this one, the Hooke's law for shear, by writing this new relationship between the stress in shear and the strain in shear. Okay, so let's see what we get. Wow, that ran a lot better and gives us something like we would have expected. Again, we're magnifying the displacement a lot. It's actually not nearly as much as it's showing in here. And the x displacement at the far right corner looks like it is 1.4 e minus 9, which is about half of what we would have expected we'd get from our calculation. Oh, wait a minute. Not 140 e minus 9, 1.4 e minus 9. That's way off. Okay, so now we want to go check what we did. We didn't put in the right Young's modulus. We have 200 times the Young's modulus we wanted, and that's why we had 1/200th of the displacement we were expecting. Okay, so at 1 E9 for the Young's modulus, we do indeed get this 280 nanometer displacement on the top surface in the x direction like we were expecting. All right, let's test some other stuff out. We were expecting that we would have a uniform shear stress and strain in this in this example. So we expect that the shear strain everywhere is 2.8 E minus 6. Can we report that? Probably the easiest way to tell if that's uniform is to look at a plot of it. So let's add in a contour plot. Maybe we'll replace one of these. Oh, actually, let's have a look at what the plots we have so far. We've got an X displacement plot, and this is on the back surface and the front surface. Those should be, or the middle surface, those should be the same. You could just click another button to go and look at the results, but it runs so fast that you may as well just run it again. What a time to be alive, right? So we've got no displacement on the bottom, and then it linearly moves up to a displacement of the max of 280 nanometers in the top. We don't have any sort of arcing of this. Seems pretty uniform all the way throughout the middle there, and exactly the same on the z equals Lz over 2 surface. So no difference in those things. Let's have a look at some other parameters. So what if instead of the x displacement, we have a look at the y displacement and z displacement? Now we expect these to be just 0. What do those look like? Looks kind of funky, but it's at E minus 15, so that's just 0. We're just seeing numeric precision there. And this one, E minus 16. Yeah, so no displacement on this thing in the y or z directions. That's good. What else? Well, let's have a look at the strains. So how about gamma yx, and let's look at the tau. Oh wait, xy is what we called it. We put it in alphabetical order. Sxy. Yeah, let's see. So this is a constant 2.8 E minus 6, as we expected, and the stress should be exactly the one we put on the top surface. Yeah, that's 1,000. What about the other stresses? The other stresses should just be 0. So let's check that out. Sxz and Syz on, how about z is equal to Lz over 2 again? Do we have any stress in those directions? Nope. And no. So for stress, this is basically 0 because the stress magnitude is more like 1,000. So to go to 1e minus 4 is 10 million times smaller, so basically 0. Whereas the strain, we only had a strain of 2.8 E minus 6. So to go to 10 million times smaller, we're in like the E minus 13 range. So that's why the 0 strain was a lot smaller than the 0 stress situation. So let's explore how we modify this code using an example here. So this is beam thinning by pulling on it in FlexPDE. This is a situation that we've dealt with before. We have a 3 meter long by 1 meter by 1 meter steel beam, and we're going to apply a 200 meganewton force to each end of the long section of the beam, and then calculate the deformation if it's otherwise free. So if it's otherwise free, with this 200 meganewton force divided by the 1 square meter, that's 200 megapascals, divided by the Young's modulus 200 gigapascals, we should have a strain that is 1 part in 1,000. And then the deformation will be that multiplied by the length of the beam, which is 3 meters. So that's going to be 3 millimeters at the, is how much one end is going to move compared to how much the other end moves. So we can verify this in FlexPDE as follows. First, we'll change the dimensions in the code to have 3 meter by 1 meter by 1 meter, and we'll put in the different material parameters, and we'll modify the stress that we're applying on this beam to, let's see, so we've got how much? We said we were going to put 200 meganewtons of stress on this. Well, 200 meganewtons, so it'll be 200 E6 divided by Ly times Lz to get it into megapascals. Now, in this case, Ly and Lz are just 1, but just to re-emphasize that you have to divide by the area, the force by the area in order to get the applied stress. Okay, so now we need to modify the differential, the boundary condition section to make sure that we're applying this correctly. So we'll find the x equals 0 surface, which is this bottom one here. It's easier to see this with a picture. So let's kind of go back up to one of these examples so we can refer to it. Sure. And even this is not the situation that we have here, but just to refer to which side is which. We've got first 0, 0, and then the next thing is the y equals 0 surface. So we want no load on this surface. Now actually, no load is the default boundary condition, so we can specify nothing, and it'll put load u, load v, load w are all 0. Now on the right surface, the only thing we want to set there is that we have a stress in the x direction of S applied. Right. So this 200 megapascal stress is going to be applied in the x direction on the x surface. Now on the top, we'll need to modify only that x stress. So we'll say that that's equal to 0. And then on the left, we'll put that it can't move. Value u is 0, value v is 0, and value w equals 0. Actually, you know what? We'll only say that it can't move in x for now. It's not totally fixed on that surface. It just can't move at all in the x direction. Problem is, this might end up flying away in y and z because we haven't fixed it in y and z at all. So let's run and see what happens here. Okay, it didn't. It looks like the u and looks like the v displacement has ended up being pretty small because there wasn't any tendency for it to move in v, but it's not quite 0. It's sort of meaningless what the v displacement is. We can officially fix it to have no displacement in y by picking a surface that shouldn't be bothered by having no displacement in y and setting value v equals 0 there. And same thing for z. Bottom z surface just fixed to z equals 0. Bottom y surface fixed to v equals 0. Bottom z surface fixed to w equals 0. Okay, so we'll get exactly the same picture. And now the v displacement is 0 times 10 to the negative 35. Yeah, there's no tendency for anything to happen in y here with this loading condition. And we just have a displacement at the top right surface of 2.73 times 10 to the negative 3. Interesting. That's not exactly the 3 millimeters we were thinking we would get. Let's have a look at the FlexPDE deformation and see if we've accidentally put in any kind of restriction on this thing compared to what we thought. It looks like it is not able to deform in one of the directions, like it's kind of forming a rectangle on this surface. That doesn't seem very sensical. So I wonder if we've accidentally made it fixed in either y or z. Let's have a look here. Probably we could figure out which one it's fixed in by making a plot of the stress on one of the surfaces. So let's make a plot of the z stress and the y stress and the x stress on some surface inside. It looks like it's still uniform, so it doesn't matter that we picked a z surface here. Let's just have a look. Okay, so the z stress is 0. The y stress is not 0. And the x stress is the 200 megapascals that we've applied. So it looks like we've accidentally fixed it in the y direction, and that's why we didn't get quite the displacement we were expecting. Now, where did that happen? Let's see. Aha! We said value, once we set this value of v is 0 on the first surface, we forgot to get rid of that and replace it with a load of v equals 0 on the other surfaces, right? So what this did is it said on the first surface we drew, which was the bottom surface, fix it to have no y displacement, and then the right, still no y displacement, no y displacement, no y displacement. So we put this x force on it and got it to extend, but it wasn't allowed to move in y. And that's why it was a little bit stiffer. It didn't go quite as far as we expected. Now we've gotten rid of that. Remember that these boundary conditions in Flex work until you override them. So it starts off with no load in any direction is equal to, the load in any direction is 0, meaning no stress in any direction. Then we apply value of v is equal to 0, and that will apply until we change it. So if we don't go and remove that fixing of no y displacement, then it'll still exist on all of the other surfaces. So now we've gone and removed that, and we should have the 3 millimeter displacement we were expecting. There it is. And no more stress in the y direction. Okay, the next thing is to rerun the program after we change the x differential equation to be derivative of these things divided by 10. The sum of those derivatives over 10 is 0. Now this shouldn't change anything mathematically, right? But it does change the answer. Now we have 10 times the displacement we previously had. The reason is that these boundary conditions we're applying, the load boundary condition, is kind of applied in a strange way. When we say the load in U is S applied, this is specifying what the directional derivative in the x direction is perpendicular to that surface. This differential equation is kind of like a double derivative in x, right, in U. There's like a second order differential equation in the displacement. And here we're specifying the derivative of the displacement. So this is going to be the first constant of integration after we integrate this thing once, basically. Why is this a second order differential equation in the displacements? Because we're differentiating the stresses and adding that together, but the stresses themselves were proportional to the strains, and the strains were defined as derivatives of the displacements. So if you filter all this through, what we're actually solving is kind of like is a sort of coupled second order differential equation in the displacements. Yeah? So when we say a load boundary condition, what it is saying is the slope of U perpendicular to this surface, right? So the derivative of U as we leave that surface, which is telling us what constant of integration to apply after we integrate it. But it's looking at exactly the differential equation as given. So these extra divided by 10s mean that effectively we've taken the stress that we're applying and multiplied it by 10. So basically this is a plea to be careful. You shouldn't be changing around the differential equations here if you want this to still refer to the stress that's applied in the given direction. So this idea where we put the beam into pure tension by deliberately applying a load and only in the x direction and only fixing it in the x direction on the other surface is not quite so realistic, right? It would be probably more realistic to take the x equals 0 surface and say that that's totally fixed. Right, this is what would actually be modeled if we said x equals 0 is kind of fixed into a wall and we're going to pull on the other x surface. So now we have a fixed support on that surface and we're pulling on the other surface. What we'd expect is that the fixed support is going to be lowering the displacement just slightly, similar to when you had one of the axes fixed before, right? We accidentally fixed y and found that the displacement was about 10% less, like 2.7 millimeters instead of 3 millimeters. Now, what happens if you fix y and z, but only at the support, only at the anchor? Probably not as extreme as fixing y and z all the way along, but maybe some small amount of displacement different. First of all, what would you get if you fixed y and z all the way along? We can do that up here and get rid of that, return the boundary condition to 0 there. So if you fixed y and z, it should still be a square. Yep. We have stress showing up in the z. Actually, it's a little bit different across the profile and in the y direction because it's kind of able to deform in the interior of this thing. And what we have is 2.5 e minus 3 as the displacement in x. Okay, now instead of that, what we're going to do is only fix it on the very last surface, on the x equals 0 surface, not all the way around, but just on x equals 0. So let's give that a shot. Can't move in y and z on this surface only. And you see, this is kind of what you'd expect. You stretch it out, but we've got this kind of edge effect at the anchor, at the spot where this is attached to maybe a wall. And the displacement is just slightly lower than the 3 millimeters we would have expected. So the anchor in this case makes an effect that is about 1%. So it makes about 1% reduction in the displacement we would get. What do you think would happen if we made it a shorter beam? So instead of 3 meters long, we had a beam which was only 1 meter long. Well, the expectation is that we would have 1 millimeter of displacement, but the anchor is probably going to make more of a difference because overall the beam is relatively closer to the anchor. So yeah, now the anchor, compared to 1 millimeter, we've got about a 2.5% difference in displacement, 2.5% reduction compared to what we had, what we would have had if the anchor was allowing it to deform in. So the anchors make a big, well, still not much difference when you're when you have like a cube, but if you are pretty close to the anchor, they can have effects on the thing. This is one of the big benefits of using a finite element method solver to explore these problems. Not only does it help us with some visualizations of what's going on and calculations, but it also lets us tackle problems that we wouldn't be able to solve very easily unless we had a finite element method solver. So figuring out what the anchors are going to do and how much of a difference those are going to make, even though it's not it turns out it's not much of a difference, figuring out exactly what that is without the help of a finite element method solver is a really difficult problem. So the next example that's in the notes actually just talks you through the example we did before, which is viewing this pure shear static equilibrium thing in FlexPDE. We can kind of turn that back now and just go over how you modify the code again. We have a Young's modulus of 29, Poisson's ratio 0.4. It was 0.1 in all the different directions. And the applied stress is 10 newtons divided by the lengths of the side multiplied together. So this is giving us the, actually I guess we should technically say if it's applied to the top surface, it is Lx times Lz, not that it really matters for a cube. Okay, and now we need to change how we're applying this stress. So to put it into pure shear static equilibrium, we are going to say that the bottom surface is totally fixed. Value u is 0, value v is 0, value w is 0. Then the right side surface, we're going to have no load in x, no load in z, but we will have a load in y. Load v is equal to s applied. Yeah. Then on the top surface, we'll put this stress only in the x direction and not in the y direction. No stress in y. And, oh, have I gotten my surfaces confused? Yes, I've got it all backwards. So this is actually, the one that we put here is the one at x equals Lx. So we need to put this set of boundary conditions here. That's the one that we wanted on the bottom surface, y equals 0. Then we wanted this set of boundary conditions on the right side. And we wanted this set of boundary conditions on the top side, just in the x direction there. Now on the left side, we want to have no stress in x, and we want to have a stress of negative s applied in the y direction. Now it's in pure shear static equilibrium. Okay, so we should get back that same shear displacement with our 280 nanometers in x. So to recap, we put this thing into pure shear static equilibrium, and we found out that there's no axial stresses anywhere, but we have a fixed xy shear stress, and maybe we can plot the other shear stresses as well. Let's also add in a contour plot of the YZ shear stress and XZ shear stress. So we have no shear stresses in YZ, that's E minus 4, and in XZ, also E minus 4, but we do have this shear stress in XY only. So this is the condition that we called pure shear static equilibrium. You put it into pure shear, and it's going to deform like this. The axial one would have it kind of extend in one direction and compress in the other ones, but not deform and change shape like this with planes changing their angles with respect to each other. Okay, sounds good, right? Well, let's do a bit of a thought experiment now in the extension topic here, and imagine what would happen if we set up the same situation. We took the same pure shear static equilibrium cube that we've got, but we put our axes somewhere else. So we just arbitrarily said, you know, rather than lining this up exactly with X and Y, let's line it up so that the X and Y axes are kind of rotated compared to the cube, right? Let's rotate it by 45 degrees so that now the cube kind of goes up diagonally between X and Y like this. Well, if we do that, then the new coordinates are going to be at 0, 0 still, except this one instead of LX0, like 0.10, it's going to be moved up to LX, LY each over root 2. And then up here, we're going to have 0 in X, and then Ly times root 2. And then over there, we'll have the negative version of this thing we had there in X, but the same point in Y, and then back down there. So let's go ahead and do that. We've got a new file saved, the same thing rotated, and we'll draw the points a little bit differently. We'll start at 0, 0, then we'll go to Lx over root 2, Ly over square root 2, and maybe we'll call this original bottom, where we're going to fix it. Then we'll take a line to 0 in X and Ly times square root 2 to go to the top surface. And this line displacement will be the original right side. Now we'll modify the next displacement to be same as this one, except negative in X. And then we've got a line to close. So this one here is the step from this part to that one will be the original top surface. And then the last one will be the original left surface. Okay, so let's see what we would set up for the boundary conditions. It's as stated originally. We're going to need the bottom to be fixed. Yep, that's fine. But we need to write these stresses that we're applying in terms of their X and Y components. So this stress that was along the original bottom has a 1 over root 2 of its value applied in the new Y direction, and a 1 over root 2 of its value applied in negative, the new X direction. So we need to apply this differently. We've got, oh wait, sorry, the bottom is fixed, so we don't apply stresses to that, but we'll do something for the right-hand side. The bottom is going to get whatever stress it needs to hold the thing still. But this right side, we need to put a stress in the positive Y direction of not S applied, but S applied over square root 2, and then in the negative X direction of S applied over square root 2, but negative. So again, negative X direction. Now on the original top surface, we are going to have, so we're going to have something like this on all of the surfaces, right? Because they're going to be 1 over root 2 components in X and Y. So we'll just copy this line and put it on all of those different directions, and then figure out what's positive and what's negative. So the original right surface, this one, has a negative X component and a positive Y component. The original top surface will have a positive Y component still, but we're switching the X component to positive, right? So that thing is now pointing in the positive X direction. And now when we go down here, the X component is positive, and the Y component becomes negative. So this should now be exactly the same situation as we previously had. Let's have a look. Okay, so it's a little bit strange to see because it's kind of rotated a bit from before, but it looks like we've got a cube which is still going into pure shear static equilibrium. This should be just a rotation of the previous situation that we were getting. Let's have a look at that. So we're going to rotate this thing. If we look at just the top, then, yep, looks kind of like that. And this one, yeah. So exactly the same deformation, but with forces applied in components in a different axis. Okay, so what? What's the point? Well, something else is a little different about this setup. So here's the original one, and remember that we had only XY shear stress. It's in pure shear, right? Because it's deformed from a cube shape into this pure shear deformation. So we had only XY shear stress, makes sense. What about this new one? Also did this pure shear deformation, so we have only XY shear stress, right? Because we just rotated the whole thing. Well, it turns out actually there isn't any XY shear stress on this thing. What? What happened? Well, we have now, if you look at this setup here, what do you have? On this surface, we've got some axial stress in X and Y, so kind of like a pushing stuff there and then there. The net result is pushing in and pulling out in the Y direction, pulling in the Y direction there, and kind of compressive in both the X directions. So in fact, that's what's going on here. So we have an X stress, which is negative 1 kilopascal, uniform compressive in X, and uniform tensile in Y. Wow. So this means that the shear stress we were applying in this pure shear static equilibrium case is actually totally equivalent to a pure tensile Y stress and pure compressive X stress if we rotate the thing by 45 degrees. We rotate our frame of reference by 45 degrees. So when we have this pure shear static equilibrium case, if we look at the thing from a different frame of reference, what was pure shear in one direction is actually just tensile and compressive in another direction. So it turns out that for any rotation angle of reference frame that we use, we can find out what the new stresses in X and Y will be and the new shear stress in X and Y in 2 dimensions by using this set of equations. So this is not something I'm going to prove, but I will show you how it works. The angle that we're talking about is rotating the x-axis by theta around z. So rotating x and y around z in the counterclockwise direction, the usual plus z rotation direction. So the rotation we did here is a negative pi by 4 rotation because we rotated it clockwise. What you do is you put in the original stresses as the parameters of this set of equations, and then you put in the angle that you're going to rotate it by theta, rotate the reference frame by theta, and then this tells you what the new stresses will be. So we can check for the one that we put in. We had originally sigma x and sigma y is 0, and a shear stress of 1 kilopascal. Then we rotated it by theta is negative pi by 4, and we found this, 1 kilopascal compressive in X, 1 kilopascal tensile in Y, and no shear stress. So you can confirm that for yourself by substituting into these equations for the theta, the sigma x and y, and the tau xy, and that it does indeed work, at least for the case that we tried out here. Or you can do this in Maple. So if you don't want to substitute in manually, then you can take those equations and put them into Maple and put in the original parameters and see what we get. So then it seems that these work at least for the specific set of stresses that we started with and the rotation that we tried out. And you can take it on faith that they actually work in general. One way to see why the y equation should be what it is, notice that it's just the x equation but with an extra pi by 2 rotation. Well, that's because whatever stress we're getting in y right now should be whatever stress we would get in x if we were to rotate the frame of reference by another pi by 2, because after doing that, the x-axis will line up with where the y-axis is currently, yeah? So that explains why we have this extra pi by 2 thing in the relation between the x stress equation and the y stress equation. So really we just have, if we have this first equation and this equation, then we can figure out what the axial stress and shear stress is for any orientation. That lets us figure out what the y stresses are as well. Now, what does this look like versus theta? Versus theta, a plot of sigma x versus tau xy, the new stress that we're going to get in x and the new stress we're going to get in xy, the shear stress and axial stress versus angle, turns out to be an equation of a circle. We can see that by first subtracting off the constant term in the axial stress, and then once we've done that, we can square the axial stress term minus that first constant that it has, and then square the shear stress term and add those together, and we get something that doesn't depend on theta. So this is, after you've taken the square root of that, we have a radius for this circle. The circle is called Mohr's circle of this. So Mohr's circle specifically is a plot of the axial shear stress in x versus negative the xy shear stress as a function, a parametric plot at all angles. So a plot of those things that you would get for all possible rotations of the frame of reference. And it tells us some interesting stuff. So it shows you that there is an angle at which you have no shear stress. And that angle is the one where you have a maximum in axial stress. There's another one where you have a minimum in axial stress and also no shear stress. Another thing, the plot of the kind of circle equation here is going by 2 theta. Why is that? Because the cosine sign in these equations are not cosine sign of theta, but they're cosine sign of 2 theta. So that means that we need to increase theta by pi by 2. When we do that, to go from the x stress to the y stress, we are taking this thing through a rotation of pi in sine and cos there, right? So that will go to the other side of the circle. So what you can actually read off both the x stress and the y stress of this circle from any point. You go at some point here, and it's telling you the x stress and negative tau xy with its horizontal and vertical values, and the opposite side of the circle over here is telling you the what the y stress will be at that same point. Oh, I've actually labeled it wrong. Dang, it's not actually the negative y stress. It's just the value of the y stress at this particular angle and tau xy. So let me fix that. All right, there we go. So we've got it now labeled that the location here is the y stress that you would have there, and the location here is on this side of the circle is the x stress. So this means we've got a point, there's some theta where we should have a maximum x stress and a minimum y stress, and the difference between them will be 2000. So these stresses, the maximum and minimum stresses you can have in the situation for some rotation, are the principal stresses. If you end up with a rotation, you look at it from a perspective where you have no shear stress, you'll always have the extreme values that you could have for the axial stresses at that same orientation. So these principal normal stresses of the object as it's currently for the particular loading of that object occur when there's no shear stress. All right, so this is really just an expression of the idea to help explain what shear and axial stress really mean. When we put a thing into pure shear static equilibrium, there's some other orientation where that same loading condition could be achieved with just normal stresses. This is very important if you're looking at failure of materials, where you've got, let's say, a brittle material that is much weaker in tension than it is in shear or in compression, because the pure shear that we have in one orientation turns out to be tension and compression in another orientation. So if you take a brittle material and you put it into pure shear, it will tend to cleave at 45 degrees off from the direction of the shear forces, because that's where it ends up being in the highest tensile stress. Okay, So definitely check out these videos from Efficient Engineer and other videos that you can see on Mohr's circle. These are some amazing visualizations of these things. I'll put the links down in the description. Thanks for watching, and I'll see you in the practice problem video.